Okay, I guess I can start. So my name is Martti Kaura, and I'm from the Tampere University of Technology in Finland. And the title that I gave to this school is Multipolar Nonlinear Optics of Surface Bulk Materials and Nanostructures. And I have this feeling that I got the dream spot in the program right after nice lunch. There's nice weather. I think some people went out for hiking and stuff like that. But let's start it. So this work come from, this is Finland. If you don't know where Finland is, I can't help you, but Sweden, Russia, and so on. Helsinki, Tampere is here about 150 kilometers north of Helsinki. It's a city between two big lakes, and this is the way it looked this winter, almost no snow, just for a while some snow. And about let's get this out of the way. So this talk is based on some very, let's say, general things, basic concepts, but there's also a connection to the work that we have been doing in the past 10 or 15 years. And these are just some of the collaborators from my own group, our Optical Electronics Research Center, then other parties in Finland and other countries. And the funding for the work we do it has been coming from the Academy of Finland, which is the agency for basic research in the country. So why would we care about multipole effects? I worked on these effects about 20 years ago. And then when I moved back to Finland, to Tampere, I thought I want to start something completely new. And at that time, nonlinear optics of nanostructures was sort of a fresh topic. Nobody was almost working on that. So we thought, let's start on that. It just so happened that we struck on these multipole effects all the time. Any new stuff we started, they were there somehow in the game. So I guess that's my fate in some sense. So here, there's a connection to metal nanostructures, nonlinear, if you want, nonlinear metamaterials, and so on. But let's say from a broader point of view, so when I say multipoles, I refer to magnetic effects and quadrupole effects in the optical response of materials. They play a role in optical activity, so let's say polarization, rotation of chiral materials. Certain rare earth ions have very strong magnetic-dipole transitions. Split ring resonators, they are very fashionable in the metamaterials community. And they have so-called magnetic resonances. Here, this is so-called a dark mode of a dimer. So it's like a quadrupole, so two dipoles out of phase. The other interesting thing is that if you want to get directional emission out of a nanoscale source, you had to rely on interference between, let's say, a dipole source and a higher multiple source. There's no other way. The other interesting possibility is that these magnetic and quadrupole effects, they might make it possible to get a second-order nonlinear response from centrosymmetric materials. And finally, there's been a debate about what type of a role they play in the origin of the nonlinear response of metals. So quite a few reasons to study these effects. And this is the outline of what I'm planning to present today and tomorrow. So I'll start with basic concepts, and so electric-dipole and higher multiple effects in nonlinear optics, surface and bulk effects, symmetry issues, especially in second-order nonlinear optics, and then how this term multipolar is used in slightly different concepts. Here, I'm probably going to repeat stuff that you know, but I think it doesn't hurt to repeat things. And at least you'll get a unified set of notes on my talk this way. And I'll try to bring some new aspects to the stuff that you might know already. Then I have planned this to have a break in between. So after about 1 hour, we'll break for 5 or 10 minutes. And then after that, I'll talk today about separation of surface and bulk effects, so-called effective polarization, a new technique which, well, not so new anymore, but a technique which we call two-beam second-harmonic generation. Then some model samples, bulk glass, and metal, so actually gold films. Then I'll try to end up with some open questions and present challenges on this topic. And then I have another 2 hours to cover tomorrow. So then we'll talk about second-order metamaterials or metal nanostructures, how we hit these multiple effects because of surface defects of the samples our collaborators are able to make, how we have been able to reach the electric dipole limit in the sort of the effective response of the samples, a number of mechanisms that can be used to enhance the nonlinear response, and again, some open questions and challenges. And finally, then the second talk tomorrow would be about the individual nano-objects, where the idea is that we use polarization-based nonlinear microscopy to address these individual objects. Especially we use so-called cylindrical vector beams, radial azimuthal polarization. Then, if there's time, I will talk about the concepts of mode and resonance in the context of nanoparticles. And finally, some still, let's say, open questions and present challenges. Okay, so let's start with the basic concepts. So about how light interacts with matter. So we might have light coming in, it hits a piece of material, then usually mainly the electric component of the electromagnetic field, it puts the charges in the material moving, you build up oscillating dipole moments. Macroscopically we say that we polarize the material, and these oscillating dipoles, they emit radiation, and therefore whatever comes out of the material is somehow modified by the presence of the material. So we have an incoming oscillating field, we'll build up an oscillating polarization, we get radiation, which then somehow modifies the field. Suppose we have a time harmonic field, and we are in the, let's say, regime of traditional linear optics. Therefore, then the polarization scales is just directly proportional to the incoming field. We have oscillations at the original frequency omega, and when you put all of this together, you get index of refraction and things like that. So this is how your eyeglasses, actually how your eyes work, and things like that. Of course, if you hit any system hard enough, the response becomes nonlinear. Often, not always though, you can expand the polarization as a power series in the incoming field. And now, if you just look at the second order term in this expansion, we square this one, we find out that our polarization is going to contain oscillation at the second harmonic frequency. And this is a source of radiation, so out comes light, at least with some luck, at the second harmonic frequency. So in terms of the photon energies, we steal 2 photons out of the fundamental beam and produce 1 photon at the second harmonic frequency. In third order, we get certainly third harmonic generation, but we also get the response at the original frequency, which is gives rise to the nonlinear index of refraction and things like that. And most of the stuff I'm going to cover is related to second harmonic generation. But of course, things are more complicated than what I just showed there. So the field, polarization, they are vector quantities. And even in the linear response, it's possible that the polarization does not point in the same direction as the incoming field. There's a font problem. This should be a sort of a dot product. So in terms of the components of the tensor, a J component in the field can produce a response in I direction. In second order, we have the second order susceptibility tensor. We can use tensorial notation. So basically, we use the input field twice to produce, or input vector twice to produce an output vector. So we have J and K components of the incoming field producing a response in I direction. So clearly, these effects, both linear responses, second order responses, or any nonlinear responses, they can be polarization dependent. So this tensorial notation, you probably know that what this means is that if the incoming field is x-polarized, and if it happens that this material has a tensor component yxx and nothing else, then the source polarization will point in y direction, and the output light would be y-polarized. This is nasty because we use the word polarization in 2 different contexts, for the response of the material and the direction of the electric field. But that's a problem we have to deal with. By the way, I brought my green laser pointer. This is a nonlinear optics workshop or summer school. Now, the structure of the tensor and that was discussed already yesterday. It depends on the spatial symmetry of the material. So we have to look at the symmetry group of the material. And then, for example, in the linear response, if we have an isotropic achiral material, so isotropic looks the same in all directions. Achiral, no handiness. Then there can be no polarization dependence, and that's easy. However, if the material is anisotropic, then the response in, let's say, x direction can be different than in y direction, and we get birefringence, and if you look at the absorptive part, we get dichroism. And then, if you look at nonlinear response, we look at all the possible symmetry operations. Then, with some luck, we can usually kill a number of the tensor components. And if we cannot kill them, we can find that certain tensor components depend on each other. They could be equal with an opposite sign. There could be a factor of square root of 2, square root of 3, or things like that, depending on the symmetry group of the material. And then, if you study nonlinear optics, this is the, let's say, probably one of the basic, most powerful rules. If your material is centrosymmetric such that inversion operation is a symmetry operation. Inversion means is that if once you fix the origin in your material system, and then if you change the sign of the coordinates of all the atoms, the systems look the same, and it turns out that the electric field, the polarization, they transform the same way as the position vector. And then if you do the calculation, it's in the inverted coordinate system, so minus p depends on minus e squared, which is e squared, which is the original definition of the polarization. You compare this one and this one, you find out that the vector can be its opposite only if the susceptibility vanishes. So no response. Therefore, people who are developing second-order materials, they are looking for, first, non-centrosymmetric units. This is a molecule which has broken symmetry in this direction. There's a molecular dipole moment. And furthermore, you have to order these units to break the centrosymmetry in the macroscopic sample. And again, in molecular nonlinear optics, you will pole the sample so that the molecules roughly point, let's say, upward. Another interesting thing is that your symmetry is always broken at the interface between two materials. And therefore, second-order effects, second-harmonic generation, and even more some-frequency generation, they're very nice probes to study surface effects, let's say the ordering of molecules on a substrate and things like that. Okay, so this is probably pretty much things that you have heard before and you already know about. Then a few other things. Covers all the background material even for tomorrow here. So about this person, especially these optical responses, they depend on wavelength. And for example, if you take any material, you usually find out that the index of refraction grows for shorter wavelengths because you get closer and closer to UV resonances that any material has. And furthermore, if you look at, let's say, a quantum mechanical model of the second-order susceptibility, you find out terms like that you have these transistor dipole moments between different atomic or molecular states here, and then you have these resonance denominators. And therefore, for example, if you look at some frequency generation where you tune omega 1 close to this transition from A to B, and furthermore, omega 2 close to transition from B to C, then you can get a small number here and also here, sort of a double resonance that can really boost your nonlinear response. And then another detail that if you're looking at some of the conventions, you have so-called permutation symmetry, that in chi2 you can interchange k and j indices at the same time as with the respective frequencies. And then, therefore, for second harmonic generation, this tensor must have this kj, jk symmetry. This is just a sort of technical detail. The other thing that comes into the game is local field effects. And in traditional nonlinear optics, where you think of, let's say, some nonlinear units in a dielectric host, we can bring in the local field factors through the Lorentz factors. So basically implying that if you bring in an incident field, then the local field which acts on your molecule is not the incident field, but you have to scale it with this so-called local field factor. And if you're in a dielectric host, this factor is spectrally pretty flat. There's no strong spectral response. And in the end, when you put everything together, you have to include the local field factors at the input frequencies and also the generated frequency. So you get roughly L to the third power here. And then you have the atomic or molecular susceptibility, which can exhibit resonances. So the point here is that in traditional materials, you have, let's say, to the lowest order approximation, you have spectrally flat local field factors, and then possible resonances in the atomic or molecular responses. Okay, all what I've told so far is based on the idea that we can describe the nonlinear responses or the material responses within the electric-dipole approximation of the light-matter interaction. It turns out, however, that if you, for example, look at the light-matter interaction Hamiltonian, so certainly we have the leading term, which is the coupling of the E component to the atomic or molecular dipole moments. But then you also have, sometimes you take into account coupling of the B field to the magnetic moments and coupling of the gradient of the E field to the quadrupole moments. As an order of magnitude, these interactions are expected to be weaker than the electric dipole interaction, but then in some cases you have to take them into account. And then if you just keep these higher order interactions to lowest order, you have to define a number of new tensors. Even in linear optics, now I use the notation EE is the traditional susceptibility, linear susceptibility. Then we have an EM, which means that in response to B field, the material becomes polarized. EQ, in response to the gradient of the E field, the material becomes polarized. But then we also have the possibility that in response to E field, we get magnetization which oscillates at the optical frequency, or quadrupolarization. The same thing in second-order nonlinear optics. We have tensors EEE, the traditional one, EEM, where one of the fundamental interactions is through a magnetic interaction. So it could be here, either of these photons would be annihilated through a magnetic-dipole interaction. And the same thing could happen through quadrupoles. Then we can also build magnetization at the second-harmonic frequency in response of using the electric field twice at the fundamental frequency. And then if you look at the you can do quantum mechanics for this. For example, for the tensor MEE, you find out that in the numerator of your quantum mechanical expression, one of these transition moments would be a magnetic dipole moment between the two quantum mechanical states. Okay, this is a heavy slide. There's a lot of stuff here. In order to get further, we have to really pay attention to difference between electric and magnetic quantities. The key difference is that, as I think Benoit pointed out yesterday, that electric quantities are polar vectors, which means that when you do a symmetry operation, for example, they transform the same way as the position vector. Magnetic quantities are axial vectors, and we can roughly say that they transform opposite to the position vector when we are using so-called improper transformations. So improper transformations are basically the reflection and inversion which change the handiness of your coordinate system. And then proper transformations are rotations which maintain the handiness. Okay? And then electric quantities, they are polar vectors. They are odd under parity, but even under time reversal. Magnetic quantities, they are axial vectors, even under parity, and odd under time reversal. So there are key differences. And you can maybe understand that better if you look at this sort of toy model. So here we have a charge which is constrained to move along a helical path. So here's the origin for electron, and then at some point when we drive the system, the electron might be here, so that we would have a dipole moment pointing in this direction. But now, because the electron is looping this way, the magnetic moment would point along the axis of the helix. Then, if we reflect this in z-y plane, then we change the sign of the x-coordinate. And now, after the transformation, the dipole moment points in this direction, but now the charge is circling this way, so the magnetic quantity is pointing in this direction. So now we made a reflection in the x direction. We see that the x component of the dipole moment is changed, but for the magnetic moment, x component is maintained, but the z and y components would be reversed. So in this sense, opposite. What happens to the magnetic quantities is opposite to what happens to electric quantities. Okay. Then some of the things that we're going to discuss a little bit later. Chirality and optical activity. So chirality refers to a lack of reflection symmetry in your object, like my right and left hand. And the point is that if you take my right hand and if you twist that into any orientation, it will never match with my left hand. If it does, I'm going to be really very unhappy, right? Painful process. So it doesn't work. So chiral objects cannot be superimposed on their mirror images. And therefore, these objects, they occur in two mirror image forms, which are known, usually called as enantiomers. So when we think of the material structure, we know about chiral molecules. So we have the same chemical formula, which can occur in two different configurations for the atomic coordinates. And then when I talk about optical activity, I mean optical effects associated with chirality. Oftentimes people say that material is optically active, just saying that there's an optical response, which can be measured. If you take an isotropic solution of chiral molecules, linear optical activity, for example, polarization rotation, depends on magnetic contributions to the linear optical response. And then whether linear polarization, for example, rotates clockwise or counterclockwise, then depends on the handiness of your sample. So if you change the enantiomer, you change the direction of rotation. And this arises from the fact that your material has a different response to left and right-handed circular polarizations. When you're looking at polarization rotation, you are looking at the differences in the index of refraction for the two circular components. Then, of course, if you look at the absorptive part, you get circular dichroism. So absorption coefficients are different for the two circular components. And indeed, these effects, they change the sign between the enantiomers. Another way to rotate polarization is the Faraday effect, which in principle can occur in all materials. But of course, people are working hard to find materials that would have a strong Faraday effect. And what happens in the Faraday effect is that you apply a static magnetic field across your material along the direction of propagation, and then for example, linear polarization would be rotated, even if the material itself is isotropic and so on. And it turns out that the Faraday effect can be interpreted as an EEM time nonlinear response, where the magnetic interaction is at the zero frequency. So it's the analog of the electro-optic effect. And Faraday rotation, it depends on the relative orientation of the wave vector k and the magnetic field. And this is a key difference between optical activity and the Faraday effect. In optical activity, the symmetry of your material is broken. There's handiness. And this handiness does not depend on the direction of light propagation. And therefore, if you go in, you rotate clockwise, you come back, you still rotate clockwise, so you come back to your original state of polarization. In the Faraday effect, when you're coming back, the relative orientation of the k vector and the B field has been changed, and therefore if you go in, you rotate this way, you come back, you rotate in the other direction, I mean relative sense, so you can end up here, which is the basis for Faraday isolators. You can isolate, let's say, your exponent from your laser. So optical activity is a reciprocal effect. Faraday rotation is a non-reciprocal effect because of the presence of the magnetic interaction. Okay, so let's get back to nonlinear optics. Here we are looking, let's just look at second harmonic generation. And let's use all these tensors that we have defined. So we have the EE tensor, and we're looking at the polarization component in I direction, right? And then J and K mean that we have to take into account the J and K components electric field. This is traditional electric-dipole nonlinear optics. Not much special happening here. Then we have the EEM tensor. And we look at the I, J, and K components of that tensor. So J is connected to the electric-dipole interaction. So we use the J component of the electric field vector. And then K is connected with the magnetic interaction. So we use the K component of the B field, right? Okay. Now the key difference is that the B field is an axial vector with different symmetry properties than the electric field. Then for the quadrupole interaction, we actually have 4 indices here. So there are 2 indices, K and L, which are connected with the quadrupole interaction. And so J goes with the electric field, K goes with the component of the gradient, L goes again with the component of the electric field. And now it turns out that gradient is also a polar vector. So here, this tensor, the quadrupole tensor, it's actually very similar to the third-order susceptibility in conventional nonlinear optics. We can use similar symmetry rules that we know from traditional third-order nonlinear optics in order to look at the quadrupole interactions. But of course, we know that the symmetry properties, in traditional nonlinear optics, the symmetry properties of second-order effects and third-order effects are very different. And if we just put all of this together, you find out that the symmetry properties of these magnetic and quadrupole tensors are very different than those of the electric-dipole tensor. And therefore, electric-dipole forbidden effects can occur, and at least in principle, there's a possibility that we can do second-order nonlinear optics in centrosymmetric materials. A very interesting possibility. The question is how to make these effects strong, of course. Okay, let's go to a very simple case. An isotropic material, which means that you have full rotational symmetry in all 3 dimensions, so you can rotate the sample into any orientation, it looks the same. Then you can go to the tables in let's say, Bob Bodge's book or some other tables. Actually, Bodge's book doesn't have the isotropic symmetry, I think, for second-order response. Or is it there? Probably not. Okay, but you can find some old papers where people looked into this in the 60s. You find out that isotropic materials, when you look at third-rank tensors, polar tensors, actually third-rank tensors, there's only rotational symmetry. There's only one independent tensor component, and that's XYZ, which is equal if you maintain the cyclic order of the indices, but then if you change the cyclic order, you get a minus sign here, okay? This means that if you look at second harmonic generation, where you have to take into account the permutation symmetry, then these two, they have to be equal because of permutation symmetry, so the whole response is killed. So no second harmonic generation in isotropic materials. And of course you can kill this also because of centrosymmetry. MEE, we can require that this tensor has permutation symmetry in the two last indices, which are both related to electric-dipole interactions. We can kill also this tensor. But then EEM, here, at the fundamental frequency, we can expect that we're going to be able to tell a difference between an electric-dipole interaction and magnetic-dipole interaction. And therefore, this tensor could be non-vanishing with this one remaining tensor component. For the quadrupole tensors, so fourth rank tensors, again, if we have full rotational symmetry, and even with or without centrosymmetry, we get the traditional rules that the non-vanishing components have indices, well, any index occurs twice at least. So IIJJ, IJIJ, IJJI, and so on. And the sum of these components is then the diagonal component III. Okay? Then furthermore, about if we now use these rules for the electric-dipole nonlinearity, then we have the possibility that we have this tensor component available that depends on the component x, y, z. As I pointed out in the previous slide, second harmonic generation is forbidden. And furthermore, in order to break the centrosymmetry, in order to maintain this tensor component, we need chirality, so handiness. Okay? So if we want to do electric-dipole nonlinear optics in isotropic materials, we need two things. The sample must be chiral, and we have to do something else than second harmonic generation. And we can try to do some frequency generation. And the first attempt for this one was already from 1966, almost 50 years ago. So really, let's say, very early days of nonlinear optics. And it turns out that when you put all of this together, you find out that the vectorial source polarization for some frequency generation here depends on this effective susceptibility, and then you get a cross product between the vectorial fields at the two input frequencies. And this first experiment was done in an arabinose solution. Arabinose is a sugar, and sugars they are usually they have handiness, and they did measure a response. These experiments have been repeated in the early 90s by the group of Koroteyev Nikolai Koroteyev at Moscow State University, Russia, and they measured the same effect. And then actually Ron Shen came back to this in the early 2000s and sort of challenged the old work. And things that may have gone wrong in the old works is that, I mean, these sugars, they tend to crystallize, so it's not clear whether they were true isotropic solutions or maybe contained some small crystals in the sample that could then change the interpretation. Okay. Then, furthermore, if you put things together, when you take into account these multipole effects, we have sources, we have the dipole source, magnetic source, and quadrupole source. And somehow we have to try to take all of those into account. And the traditional way of doing that is to define an effective bulk polarization. So you interpret all the effects in the end as an electric-dipole effect. So this effective polarization includes the true dipole polarization, Then it depends on the quadrupolarization, so you have to take the sort of the dot product of the quadrupole tensor with gradient, and then you have the magnetic sources here, so you have to calculate the curl of the magnetic sources. And then when you do a few pages of calculations from here to here, you find out that your effective polarization can be expressed in this very generic form. There are three parameters: beta, gamma, and delta prime. The reason that you have a prime here is a historical reason, and I'll come back to this issue a little bit later. This beta, it depends on a certain combination of the components of the quadrupole tensors. So we have the EEQ, QEE tensor and the certain components from there. Gamma depends on the quadrupole tensors and also this EEM tensor, which is also non-vanishing. Delta prime depends also on the quadrupole tensors and this EEM magnetic tensor. So this is what you get just by going through all the arguments for isotropic materials. And then I'm coming to, so this is sort of the basic background. I'm actually way ahead of my schedule. But some of the issues which are in my mind that you should remember if you start talking about this, let's say, multipole effects. This term multipoles is used in different contexts. They are related to each other, but somehow sort of different still. And one important difference is because we are moving towards nanostructures, is that so far I talked about basically the atomic or molecular level light matter interaction, so you can build up the Hamiltonian, do the quantum mechanics, define these different types of multipolar susceptibilities that describe how your material works. But then, of course, when you get into nanoparticles, you have to be concerned about scattering theory, and especially if you have spherical particles, then this problem was solved about more than 100 years ago by Mie. So Mie scattering theory. And the important thing in Mie scattering theory is that even if you assume that the atomic level interaction is purely dipolar, you forget all these interactions. In the end, you find out that the scattered far field contains terms which look like gradients for electric or magnetic, dipolar, quadrupolar, magnetic-dipolar, magnetic-quadrupolar, and so on sources. So we can expand the scattered far field in terms of these various multipole terms. And this is based on the fact that due to the spherical symmetry, spherical function, they form a basis. So no matter what you measure in the far field, you must be able to expand in this basis. And this basis then can be connected to scattering patterns which are related to different types of multipolar sources, okay? And this happens even, I emphasize, even when the low-level interaction is purely dipolar. The other thing is that if you take this a little bit further, your source does not have to be a spherical scatterer. If you go outside of your source region, you can still always expand your scattered field using the same expansion. And therefore, this expansion is valid for any confined source. So for example, if you use focused laser beams to address, let's say, a thin film or something, whatever you measure, then in the end, you must be able to expand in terms of these scattering multipoles. Okay. Then another thing that's I think is important to note in the context of metamaterials. So this is this is one of the favorite structures for the metamaterials community, as the split ring resonator. And if you excite this using light which is polarized this way, then you can force the charge to oscillate along this path, right? So at some point, your charges might be at the ends of the whole structure, and then certainly you have a dipole moment here. Nevertheless, the community usually emphasizes the magnetic response of these structures. And sure enough, when the charge moves back and forth here, you have a nanoscale current, so you're going to have a magnetic moment that oscillates out of the plane here. So in principle, you can go inside your source, you can calculate the electric and magnetic moments of your charge and current distributions, and then start making statements about whether the response is electric or magnetic. The problem is that if you go to any book of electromagnetism, if your system has a non-vanishing dipole moment, then the higher moments, magnetic moment, quadrupole moment, and so on, they depend on the joint of origin of your expansion. And therefore, if your system has a dipole moment here, like here, it's not clear whether you can say that there's a well-defined magnetic response or quadrupole response. And I think people are aware about this. Harald Giesen had a paper a few years ago where he said that you can actually interpret this magnetic resonance or response as a response of a higher order plasmonic response, whatever that means. And the other thing is that, of course, if you don't have a spherical symmetry here for your scatterer, then you cannot do the multipole expansion of the field, not necessarily using the spherical expansion. There could be something more happening in the near field and so on. So you should be really careful here. But of course, people have used this structure for very interesting experiments. And finally, if you are looking at molecular structures, people talk about multipolar structures, and with some luck, once Isabelle Ledoux gets here, she might talk about these things. And this is related, and I think you talked about that yesterday, that you can, this is connected to the finding so-called irreducible representations of tensors. And then you find like so-called dipole part, scepter part, and so on. And this molecular structure is interesting. You have a threefold symmetry. So this has no dipole moment. The dipoles cancel. But this structure is still non-centrosymmetric with a second order response. This structure is known as octupolar molecule. And it's octupolar or octopolar depending whether you talk to Joe Zus or André Persson. So 20 years ago they had discussion about what's the proper word here. Okay. I'm done with my background part, so there's plenty of time to discuss here. So basically, I think I might have a little bit more in the second part, so my suggestion that we have a 10-minute break. We can break. Okay, I think that the break of 10 minutes is over, and I just heard that I misrepresented the book of Bob Boyd because I'm always thinking of the first edition, which is, I have all the editions, but still, I mean, I have less time to look at the books these days than I should. So the latest editions include full sections on chiral media and these issues. So isotropic materials are covered. Okay, so that's good to hear. So let's move on. Let's now try to put the stuff that we discussed before the break somehow together to discuss surface and bulk contributions in the second order response of materials of, let's say, very high symmetry. So this is where we stand now. So basically, let's say that this is an isotropic and centrosymmetry material, like a piece of glass or something, a similar amorphous material. Then, from the symmetry rules, we know that at the interface between air and let's say glass, we are going to have an electric dipole allowed surface response. And the symmetry of the surface is such that we have full rotational symmetry about the surface normal, the z-axis here, but not in 3 dimensions. So we have 2-dimensional rotational symmetry. In the bulk, we have 3-dimensional rotational symmetry. So we cannot, and if we assume also centrosymmetry here, we are not going to have any response within the electric dipole approximation. But we can have secondary polarization due to this EEM tensor and EEQ tensor. And then furthermore, in principle, we could have this nonlinear magnetization from the MEE tensor and nonlinear quadrupolarization from the QEE tensor. These are the tensors we defined earlier. Of course, in principle, it's possible that we would have some other type of multipole response which is at the surface region also. But depends on how you describe that. It turns out, however, that whatever happens at the surface can be included in the effective electric dipole response, at least within the present knowledge. So in the bulk, to take all these higher multiple response into account, we can calculate the effective polarization, which we already discussed before. So combine the dipole, quadrupole, and magnetic sources into one effective polarization. Okay? And then I'm using the same slide over again that I had last time. But the point is that when you calculate this effective polarization, you come up with these 3 parameters that define the bulk response. And these parameters, when you do this calculation from here to here, you already take into account all these details of the symmetry operations. For example, the fact that actually this MEE tensor vanishes because of the permutation symmetry for second-harmonic generation. Okay? And so on. And then you have these certain components of the quadrupole tensors and so on. So you can put everything together. And then if you start characterizing your bulk medium, for example, the question is that how are you going to be able to measure these parameters? And to have a closer look at this expression, let's use some of the symmetry rules again. So the material is isotropic, and it turns out that in an isotropic material, del dot E is always vanishing. So this beta term, although it's formally here, beta parameter is non-vanishing, but this interaction does not occur due to the symmetry of the material. Then another interesting thing is that this gamma, which is a bulk parameter, it turns out there was a paper from I think about 1982 by John Scheib and George Stegeman. They showed that in experiments that you can do in the lab, this gamma term contributes to the effective surface response. And you can somehow see it from the fact that this depends on the gradient of the E times E. So when you start integrating the signal that you get, this integrates back to the surface. Okay? Somehow it makes at least hand-wavy sense. And finally, this delta prime is so-called separable bulk contribution. This is something you could try to measure in an experiment. And then furthermore, at the surface, you have this effective electric dipole tensor, which could have contributions from the dipole interactions and some higher multipole interactions. But in some sense, we are going to assume that it fulfills the symmetry rules of the electric dipole tensor for a surface symmetry. And when you look at the details of all these treatments, you find out that the effective surface component with indices z, z, z is the true surface response with the same indices plus gamma, which is the bulk parameter. Okay? The same happens in zxx, so it's the true surface parameter component zxx plus gamma. But this gamma does not contribute to the xxz surface component. And by the way, the fact that you have these components at the surface, that follows from the fact that you have a full rotational symmetry about the surface normal. Your symmetry group is C infinite V. And when you look at the tables and go through the operations yourself, this is what you find out. That you have three surface components. So in an experiment, we can try to measure these components and then this one bulk parameter. Okay? And let's first try to think of experiments that could somehow access this delta prime bulk parameter. It turns out that if you do second harmonic generation with a single beam like usual, you don't couple to this term at all. So what you have to do is that you have to bring in two fundamental beams that intersect in the medium, like here, and then you have to measure the joint signal, either in transmission or reflection, that depends on both of these two beams. Of course, each beam separately creates a signal, like in this direction or in this direction, but we go somewhere in between and look at the joint signal, okay? And then the growth of this signal, it depends somehow on the coherence length of the interaction within the bulk. So it depends on the difference between the k vectors at the second harmonic frequency, and then the sum of the this should be 2 here, but this is sort of this is the phase mismatch. And the person who worked on this a lot started from the 1980s and until early 2000s was again Ron Shen, who is really the pioneer of surface nonlinear optics. And he did a lot of different experiments trying to somehow access this contribution. So he did some frequency generation, relying on difference in the spectral response in the bulk and at the surface, taking into account the fact, trying to utilize this fact that the coherence lengths in reflection and transmission are different, and so on. But all these experiments, they had difficulties because of the material dispersion. And another thing that if you do experiments, it's extremely difficult to calibrate absolute signal levels. So if you compare signal, let's say in transmission and reflection, and you want to calibrate them in an absolute sense, that's a painful process. So all kinds of things that somehow hampered these experiments. We got this into this accidentally. We were working on thin films in order to characterize their response within the electric-dipole approximation and as precisely as possible. And we realized that in order to have more parameters that we can control in the experiment, it's better to use 2 input beams. We got some of the first data for some of the samples, and we could not fit the data with any reasonable electric-dipole surface model. And we started looking into what might be going on, and we realized that we are measuring the bulk contribution. And we got this really direct evidence of the bulk contribution by doing polarization measurements. In general, we like to do polarization measurements. And by that, what I mean by polarization measurements is that we detect certain polarization components of the second harmonic signal, and then we modulate the states of polarization of the 2 fundamental beams. Oftentimes, as you're going to see, we want to fix the polarization of one beam, for example this one, and then use a wave plate to rotate or modify the state of polarization of the other beam. So we make polarization scans, and then we can fit those into certain models and so on. And the key here is now that if you look at the theoretical expressions we have, and again work a few pages of algebra and so on, the bulk contribution that depends on the delta prime parameter, it goes as the P component as beam 1 times the S component of beam 2 minus 1S 2P, okay? And then, and you're detecting now the S polarized signal. Then the surface response depends on the just one tensor component YYZ, and it goes as 1P times 2S, 1S times 2P. The same combination as here, but here we have a minus sign. Here it depends on the angles of incidence. And now if the two beams come from the same side, we get a plus sign here. So in some sense, when we do this polarization scan, we have an in-phase contribution between the two terms from here, and out-of-phase contribution from here. So we can expect very clear signatures. Okay. But one more thing before we get into the actual experiment. There's a really interesting thing that's related to phase matching. So for the bulk signal, we have two beams that intersect within the medium, and then we create the second-harmonic signal, let's say, in some direction. So basically, in a real experiment, we use finite beams, so beams with finite transfer size. So therefore, our interaction region is going to look something like this diamond here. Then, and it turns out that this interaction is not, there's a pretty strong phase mismatch because the beams cross each other and so on. Then it turns out that when we work out the details, if you localize this interaction region deep into the bulk, in order to access only the bulk response, your integrated signal is 0 because of phase matching reasons. So you have to bring in this interaction region close to the surface. And the reason why you get cancellation deep in the bulk, it's because what you get from this triangle here exactly cancels with what you get from here. So the two parts, two halves, get out-of-phase contributions. And we verify this in an experiment. So we scan the sample through this interaction region. So we get something at the, let's say, glass-air interface, and then again something at the glass-air interface. So of course, if you look at this, you might say that, okay, this must be a surface response. But I mean, a surface response does not extend millimeters into the material. I mean, a surface response is something which is sort of localized into really a very thin surface layer. Okay. But the problem is that when we try to measure this bulk response, we have to do, we are going to be interacting also with the surface response at the same time. So that's a complication. So this is the idea how we do the experiment. So two beam second harmonic generation. We call one fundamental beam a control beam, the other one a probe beam. So here we fix the polarization of this beam. It could be SOP, maybe plus minus 45 degrees in between. And then we use a quarter wave plate to rotate the probe, to modify the probe polarization. And our starting polarization, sometimes it's SOP, sometimes plus minus 45 and so on. And we can measure second harmonic signals in the transmitted direction or refracted direction. And we used two different types of samples. A poled polymer film, which is supposed to have a really strong surface type response, and a film which is much thinner than a wavelength, so we don't have to worry about phase matching. And then just a BK7 glass. And then we were hoping that we get some type of an interferential competition between the surface response and the bulk response. And this is how it works out. This is the poled polymer sample, and here is a fit to the data using the surface model only for the reflected and transmitted signal. And you see here that both cases fit almost perfectly to the surface model. For the glass surface, the reflected signal, there's a pretty good fit, but there's another fit which is to this fit that includes both surface and bulk response, and it's slightly better. We are going to have a closer look on that in a second. And then for the transmitted signal, we are not even close to this surface model. This is the way it should behave, and we're sort of out of phase completely. And we get a much better fit using the bulk model, but it's not perfect. We can improve the fit by taking into account the interference between the surface and bulk responses. Okay? And then furthermore, when we look at the data more carefully, we can fit the data into this model. We have the surface response plus some coefficient times the bulk response. And looking at our experimental geometry, we can calculate the coherence length of the interaction, for the bulk interaction. In reflection, the coherence length is only 100 nanometers, very short. In transmission, it's 10 microns. And then, even in reflection, we get a slightly better fit using a model where both contributions are present, and we get a number for this bulk for the sort of this strength of the bulk effect, which is in some units 0.08. In transmission, we get a value for S, which is 6.5. And it turns out that the strength of the bulk response, it scales exactly with the coherence length, which is as it should be. I mean, the longer the coherence length, the more buildup you get of your coherent signal. So this works out nicely. So things work as expected here. Okay, then we can try to do a much more complete polarization study. And the idea is that when we look at the isotropic surface symmetry, the symmetry of the sample for the surface part and the bulk part, it turns out that we can always express the S-polarized signal in this way and the P-polarized signal this way. So in an experiment, we can try to measure these parameters F, which represent coupling of the signal to the P and S components of the fundamental beam. Okay? And the reason that we don't here have, let's say, P-P combination, it's because of the symmetry of the sample. But then we have P-P input here in the P-polarized signal and so on. And these parameters here, they depend on these tensor components that we are trying to determine. Okay? So basically, if we do enough studies where we somehow relate these F parameters to each other in a reliable way, we can work backwards and then in the end to solve these tensor components. So what we have to do is that we have to do a set of measurements playing with the polarizations of the fields in order to get unique solutions for these F parameters. And once those are known, we have a set of linear equations to solve for the actual tensor components. Okay? And again, to make a long story short, this is what we get. We normalize the response to the XXZ component of the surface tensor. That's one. And then what we get here is that the ZXX component of the effective surface tensor is 0.49. I mean, let's say 0.5. And the ZZZ component of the surface tensor is 6.4. And then the bulk parameter delta prime is about 1. And then finally, what we can do is that we can take all these results and calibrate our signals to a non-reference material which is crystal quartz. So we actually get numerical values for these components, and then we can compare those to earlier measurements or some theoretical models and so on. And when we do that, I mean, in the past, people have measured surface responses, and we have a good reasonable agreement with earlier measurements. The new thing is that we have been able to access this bulk contribution. And now, let's have a look on whether this really makes sense, what we have measured. And whether we can get a handle on what is the origin of the bulk response. And in order to do that, let's assume that whatever happens at the surface is just an electric-dipole tensor. So whether there's some surface multipole contribution, it can be absorbed here. So in some sense, I'm crossing out this part here. These contributions are hidden here. Now, a glass, BK7 glass, it's highly transparent. So you would expect that Kleinman symmetry is at least valid to some extent. I mean, I did not mention Kleinman symmetry in the first lecture, but the Kleinman symmetry means that you can change the order of these indices any way you like, and you get the same number. Therefore, if we only had a surface response, then these two components would have to be equal. Here, they differ by a factor of 2. And therefore, my claim is that a factor of 2 is a big difference. So clearly, Kleinman symmetry is not fulfilled here. I mean, actually, I'm not a big believer in Kleinman symmetry in any case. I mean, people take it to extremes in some cases. And there are actually papers where people have addressed how valid is Kleinman symmetry in some context. And you can measure always some deviations. But this is really far away, okay? And then in these units, if we assume that we can explain this deviation here by the presence of this bulk parameter gamma here in the effective surface response, we get that gamma would be about 1/2 again also. And then delta prime, which is not on this slide, it was from the previous slide, it was about 1, okay? So now we have estimates for the two bulk parameters. One measured through the surface response, because that's the only thing we can do. One measured directly. And then let's go to these theoretical expressions for the gamma and delta parameters. Beta is not important. And then when you look at the quadrupole part here and the magnetic part, then if you assume that the bulk parameter or the bulk response is only due to the magnetic interactions, you find out that gamma should be minus delta prime over 2, so 1/2. And this is what we measured in the experiment. So therefore, it's very tempting to say that the bulk contribution has a magnetic origin. Why? We don't know. But incidentally, at the same time when we worked on this, there were other papers where people suggested that various glasses have stronger than expected magnetic responses. But these are really vague connections. The problem that we have here now is that if you look at the quadrupole part, if the response was dominated by EEQ tensor, then gamma would have to be 1 plus 1/2 of delta prime from here. But then the problem is that for the QEE tensor, the components that appear are x, x, y, y, and x, y, x, y. And there's no fundamental symmetry rule that would connect these components to each other. So there's still sort of some remaining uncertainty. But again, if these were assumed to be equal, then the quadrupole part would have a plus sign here. So all this hand waving really suggests that magnetic effects do play an important role here. Okay, then let's move on. So we did glass. That's a nice clean sample. It's a piece of bulk glass. And then at the same time, we've been working on these metal nanostructures. Other people are working on these, let's say, the split ring resonators. We've been working on this L structure and so on. And I'll get back to this tomorrow. We've been working on this T nanodimer and stuff like that. And then when people started working on theoretical models of the nonlinear response for metal nanostructures, then a question came up that how do we describe sort of the local nonlinear response of a dielectric metal interface? Because you could somehow expect that the response from the nanoparticle is somehow obtained by integrating the local response around the shape of the particle. And in our work, we emphasized the role of the local surface response, but there were some other papers where people tried to explain the response in terms of the bulk response of the the conduction electrons of these, let's say, noble metals. And then the bulk response, you have to take into account the Lorentz force on the conduction electrons and so-called convective force. And basically, these are free electron theories, and they try to explain everything in terms of the bulk response. Bulk in the, bulk of the nanostructure, if there's any bulk. But you see what I mean. Somehow inside away from the thin surface layer. The problem is that if you take the simplest free electron theories, then this bulk parameter delta prime that you can measure vanishes. So we thought that let's have a look on this, that we know how to measure the bulk parameter, and we might get some evidence about what's going on with the metals. So the same experiment, two-beam experiment, but now using a gold film, thickness of 150 nanometers, so much thicker than the skin depth. So we are not actually even reaching the back surface or interface of the film. It was on the glass substrate. We measured the linear properties by ellipsometry in order to be able to make as precise modeling as possible, which is actually important. But otherwise, the same experimental setup: control beam, probe beam, polarization modulation, measuring a lot of stuff, and so on. Okay, then here are the first results. So this is the simple argument that if we measure the S-polarized signal, we can just look at this, what I call in-phase and out-of-phase contributions to the response. One representing bulk contribution, one surface contribution. And sure enough, when we measure the data, we can only fit the data by taking into account the bulk contribution. So here, the blue and red dotted lines are various possible surface models. The difference being whether we use, when you do surface nonlinear optics, you can define the response in terms of the fields outside of the medium or inside the medium, or some combination. And then you get slight differences from the transmission coefficients and things like that. And we took into account both possibilities. And what we can predict using the surface response also is indeed the blue and red dotted lines here. No good match. Then when we take into account surface bulk interference, we get a very nice fit to the data. Okay, so delta prime seems to be vanishing. But remember, I just said that these free electron theories say that there should be no delta prime for metals. But this problem was solved by a collaboration with John Sipe. So he modified these free electron theories by adding damping of the electrons. And then once you add damping into the hydrodynamic model, delta prime becomes non-vanishing. And furthermore, we then went on, because John Tsai provided us numerical results for these various parameters. You can use the free electron theory also to predict the surface responses. Then we did this more complete set of polarization measurements using different combinations of control and second-harmonic polarization, modulating the probe polarization, and measuring 4 different sets of data, trying to fit this into this unique set of these F coefficients, and then solving the actual tensor components from the data. It's a lengthy but straightforward procedure. The main trouble is that you have to do the experiments really carefully, 2 beams in the same plane of incidence. Everything is very, very sensitive to any misalignments and things like that. But in the end, we got results, which are here in the table. And now you can express these results in a number of different ways. For example, you could express the surface components using external fields or internal fields. We use internal fields in order to compare the numbers for the surface parameters to the bulk parameter. Of course, the bulk parameter has to be defined in terms of the internal fields, right? And this is what we get. Here's a surface parameter ZZZ, huge, 250. ZXX, which is actually within the free electron theories, there's, for metals, this ZXX surface component is actually only due to this gamma bulk parameter. Very interesting. That would be 1 in our case. We normalize here. XXZ surface contribution 3.6. Bulk parameter delta prime 2.7. Okay. So we measured the bulk parameter, no question about that, but clearly the surface effects are important also. And now you could say that, okay, ZZZ 250, it's basically 2 orders of magnitude higher than these 2 other parameters. So in practice, nothing else matters than this ZZZ surface response. But you have to be really careful, because if you used external fields, this would become much, much weaker. The trouble is, it's not trouble, but it's just a fact, that ZZZ, because when you go across the interface, it's the normal component of the field which is discontinuous, right? And in the case of metals, the Z component of the field is basically screened by the metal, and therefore, in order to account that the Z component inside the metal is very weak, you have to account for that sort of artifact by making the respective tensor component really strong. And then, in the end, what matters is that how do these tensor components contribute to the measured signals, right? In the end, you measure signals and not direct the tensor components. And then things change completely. The dominant contribution to our signals comes from the surface component XXZ, and then the bulk parameter becomes relatively really weak. But then, this is how it contributes to the dominant signal. If you look at other signals that we measure, then the bulk contribution becomes reasonable already, tens of percent and so on. So the point is that when you're doing, when you're doing surface nonlinear optics, and especially mixing in the bulk effects, you have to be really careful how you interpret the results. You can throw in numbers that say that, okay, this is the dominant contribution. Right now, people who are doing modeling of metal nanostructures, and one way to model is to indeed to take these, assume that in a nanoparticle, at each location of the interface, you have this local response, which is described by these numbers. And people are citing this paper of ours, saying that these results show that ZZZ is the dominant component. Yes, we are doing that ourselves, and we can fit our data there very nicely, but the bottom line is that when you look at what we get for a flat film, things can be very different. So you have to be really careful. And in the end, of course, you would like to build a model which takes into account all these effects. And it's doable. Some groups have tried to do it and so on. So there's no fundamental problem anymore. Okay, then, so we were really happy here that we were able to measure the surface and bulk contribution for the first time for a metal film. But then we thought that, okay, let's do another check, because when you make these metals by evaporation, there's always some surface roughness. And the film we used in the previous measurements, it was 150 nanometers thick. There's an RMS surface roughness of 1.1 nanometers and peak-to-peak roughness of about 10 nanometers, which is actually quite a bit. We made a nominally thinner sample, 20 nanometers thick, so then the RMS thickness becomes a little bit higher, 1.5 nanometers, and peak-to-peak roughness is a little bit higher. And then if you look at the AFM images of these two samples, you can see that the characteristic feature size here is smaller than here. And so in relative terms, this is much more random and rough and so on. So we thought, okay, now we have two samples with different surface structure. So let's see how that influences the response. And then we just use this simple model, the surface part and bulk part for the S-polarized signals. This is our 20 nanometer sample, the new sample. This is the old one. So here we see that the deviation from any possible surface response is even higher. And when we fit the data here using this simple model, then when we have a rougher surface for the thin sample, the surface parameter goes up by about 10%. The bulk response is more than doubled. So this is strange, where basically we think that we are modifying the surface structure, but it seems that the bulk response goes up. So something really strange is happening here. How is this possible? We change the surface, but the bulk response seems to go up. This is due to the fact that when you have these nanoscale features, you can interpret that each bump on the surface is a nanoparticle, and you can apply Mie-type scattering theory to that particle. And then when you take into account Mie theory, then such a nanoparticle could have, in some sense, an effective higher multipole response. Even though at this one location at the interface there's just an electric-dipole tensor. When you integrate over the shape of the particle, you would get, in the effective sense, let's say a quadrupole response. Okay? And we built sort of a symmetry argument for this. We idealized this bump into a sphere, and then we brought in these beams like this, a signal is going this way, and then when you look at this experiment, the experimental geometry, when you forget the states of polarization of the beams, you have a mirror plane here. I mean, this plane is a mirror plane, and then the plane of the board, the plane of the board would be a mirror plane. When you go through all the possible symmetry operations, not for the sample itself, but for this experimental geometry, you find out that the only signal you can get out of here requires that the two fundamental beams have different polarizations, and then you only get an S-polarized signal. And that is actually exactly the symmetry rules that's related to this delta prime parameter. So we end up here in a funny regime. We are trying to measure this fundamental bulk parameter due to magnetic and quadrupole effects. But then we get qualitatively exactly the same response from the fact that we have some nanostructure in our sample. So this means that we have to be really concerned about these things. On the other hand, I forgot to say that these results from the nicer film, we also calibrated these against a reference sample, and the numbers we got for these various parameters, they are amazingly close to theoretical predictions from John Sipes' free electron model. So, and the biggest uncertainty in this delta prime parameter, it was a factor of 10 higher than we hoped it would be. But the fact that there's always a surface roughness also plays a role here. That could have influenced the results there. So it's not easy, not easy. So what we would like to have, now people can make these single crystal gold flakes. Not very big yet, the size is in the range of microns, but it would be really nice to repeat all these experiments for metal gold flake that basically has atomic level smoothness. And people can make samples like that now, but not quite big enough for our experiments yet. All right. Okay, I'm almost at the end. Now some of the open questions and challenges, some things that bother me actually a lot, really a lot. This is the expression for the bulk polarization in terms of these beta, gamma, and delta prime parameters. This vanishes. There's this old paper that argues that gamma behaves as an effective surface response. And delta prime is this separable bulk contribution. And this is the form for the effective bulk polarization, which is mainly used these days. However, if you do some vector differential calculus, or if you go back to the old paper of Bloomberg from I think 1962 or 1963, you find a different expression for the bulk polarization. So basically, this part here can be expressed as a combination of E cross del cross E. And del cross E depends on, is actually beta. So this part can be contributes to a contribution which is some parameter alpha times E cross B. And then you also get a contribution from here, which looks like this here. So you get the modification in the delta prime parameter, which is here. And actually in the original paper, if I remember right, this was called as delta. And then when you went to this form, you said it's going to be delta prime. Okay. So the funny thing is that what we have now done here is that we have played a mathematical trick which completely removes this part out of the expression, which behaves as an effective surface contribution. We know that this functional form here is something which represents a separate bulk contribution. Okay? So we can measure it. And furthermore, this alpha here, that depends in the bulk fields, the electric component and the magnetic component. So there's something very, very funny going on here. So the big question is that, does it even make sense to try to separate the surface and bulk contributions? I don't know at this point. The other thing which bothers me, I'll mention it already now, is that I don't really like this approach of effective polarization. I have to check what this other slide is. It's not this one, yeah. The problem with effective polarization is that, I mean, if you take a book of Jackson, books on electromagnetic theory, you find out that you can define this effective polarization, which combines the dipole polarization, magnetization, and quadrupolarization. The problem is that sort of the treatment is based on an infinite bulk medium. What we have here is basically finite media where you have interface and so on. And then when you bring these expressions to the interfaces, how are you going to take into account, let's say, the boundary conditions for the electric and magnetic fields if you express everything in terms of polarization? If you use this expression in a, let's say, casual way, I can show an example where you get a wrong result when you try to predict what you get in transmitted direction or reflected direction. So there are certainly pitfalls regarding the use of this expression, and then there could be some more fundamental problems, as this example here shows. Fortunately, I don't know if you, some of the senior people at least here know John Shipe. He's an excellent theorist, and he's been now sort of working on a new model which would take into account in an explicit way all the different types of sources also. And it's really going to be interesting to see how that works out then in the end, so that we can separately take into account the polarization, magnetization, and quadrupolarization sources and connect those to the symmetry of the tensors and everything. So in principle, we can do a much deeper analysis maybe in the future. Another problem, what do we mean by the bulk contribution? Okay, so the bulk effects, or in general these higher multiple effects, they depend on field gradients, right? And now when you come to an interface between two media, then the Z component of the field is discontinuous. And then you have a well-defined value in this bulk medium here, and then somewhere here in what I call true bulk. And of course, then something happens at the surface layer, which has a thickness of maybe of a few atomic layers. And therefore, because the Z component has different value here and here, there's a really strong surface gradient. And therefore, if you take this surface gradient into account in this expression, you are going to get a really strong response, right? And then the question is that, is this response, which is described by a bulk parameter and surface gradient, is the bulk response or surface response? In my opinion, it's a surface response. And there are some old papers by Shen where he showed that actually when you do this in a number of different ways, you can show that this response contributes to the effective dipolar surface response. And that's fine. The problem is that when people are doing modeling, and in your theoretical models, you can give a number for the bulk parameter, and then you can do another run where delta prime is 0. And some people say that bulk effects are really strong because when they turn on delta prime to 0, the signal becomes much weaker. But it's very difficult to figure out in a number of different papers by different authors whether they let delta prime to interact with the surface gradient. If they do, I think it's wrong to say that there's a strong bulk response. So my opinion is that you should keep the bulk parameter away from the surface layer, and then just be happy with the fact that there's some effective dipole tensor for the surface. And it's going to be interesting to see when people talk to each other how things start converging and so on. What is the final understanding? So basically, this problem, some of the expressions, they are indeed 50 years old. But in my mind, at least, there are still open questions and even challenges how to do things right. Finally, this is a word of caution. So we have this possibility that we could do second-order nonlinear optics in centrosymmetry materials. Then the question is that how do we find a material with a strong multipolar, higher multipolar, so magnetic or quadrupolar bulk response? We are sort of hoping that, okay, some nanostructured materials would do the job. But then when you get a new material, oftentimes it's easy to make thin film samples, but not really extended bulk samples. Of course, depends on the techniques. And then if you have a thin film sample, then this like a really simple measurement where you measure S-polarized signals and just compare these in-phase and out-of-phase contributions to see what are the relative weights of the surface response and bulk response. Unfortunately, we have just found out that it fails, because when you start getting multiple reflections in the thin film, that actually leads to phase differences between the different field components, and therefore these two contributions, whether they're in phase or out of phase, are not so well separated anymore. And we have even showed for the case where we expect only a dipole response that when we do a measurement, we get something that looks like a bulk response, but using this a really detailed model that includes all the multiple reflections, we can explain everything using just the dipolar response. Okay, if I remember right, I'm done for today. So thanks for your attention. I'm happy to answer any questions, and we'll go on tomorrow with some related topics.